So now I would like to invite Neville Hogan to introduce Michael West Jr.
Hi there. It's a real privilege to introduce Michael West. Briefly, I first encountered Michael West when he came to MIT to work in my lab as a summer intern. At the time, he was an undergraduate in mechanical engineering at Yale, working with a colleague, Madhusudan Venkatesan, who I've known for quite some time. And he subsequently came to MIT as a graduate student, completed a master's degree under my supervision, and very recently just passed the qualifying examination. So he's now a card-carrying member of our doctoral program. So one of the things that I think you may see in this afternoon's presentation is not only is Michael able to do top quality research, but he has a passion for it that goes beyond the average. So in the course of doing his master's degree, he was working on trying to understand synergies in finger coordination during actual manipulation of flexible wire harnesses. He took on a completely separate project, working with one of my former postdocs, who's now junior faculty at University of Massachusetts, to see how do humans actually perceive stiffness without actually making contact. I think Mike will say something about that, but he's extremely active. He's also in, I have to go look this up. He's in it's an Academy of Courageous Minority Engineers, ACME. And he's a member of the Black National Society of Black Engineers and the Black Graduate Student Association. So he's actively giving back to the community, but I think you'll see that his real talent is for the research.
Thank you for the introduction, Professor Hogan. Let me share screen. So can you guys see my screen? Oh, cool. All right, so as Professor Hogan said, today I'll be talking about mechanical impedance not only in the motor action domain, but also in the motor perception domain as well. So going right into it, in our lab, we study how humans manage physical interactions. Specifically, we want to understand from a control standpoint how humans control motion so that we can implement this on robots. And in the video shown on the left, you can see humans successfully managing some of their everyday tasks, while on the right, you see some of the most advanced humanoid robots at the Dark Robotics Challenge failing to do tasks that we humans find trivial. Just traversing through a door, trying to get out of a car, walking through sand. And what makes this most interesting is when you look at the humans' wetware and hardware. For instance, humans' actuators are about an order of magnitude slower than robots. Our communication is about 6 orders of magnitude slower, and our feedback delays are about 2 orders of magnitude greater. So the question comes, so then it appears that we are doing a lot more with less. So the question comes, okay, well, what enables humans this paradox of human performance? And one solution is this idea of dynamic primitives, which are a set of innate actions that simplify the control of the otherwise complex neuromuscular controller. And the key aspect of these dynamic primitives is that they are presumed to be some semi-autonomous output of your neural control. And what that essentially means is they trigger themselves and kind of play out on their own. Professor Hogan and Professor Sternat have identified 3 of importance. However, today I want to focus in on mechanical impedance as it has been specifically proposed for managing physical interaction. Mechanical impedance is the dynamic relation between motion and a resultant force. And oftentimes it is modeled as a linear spring and a linear damper between some nominal trajectory and an actual motion. So, and lastly, I presented mechanical impedance in the previous slide as a feature that enabled humans of great physical interaction tasks that robots could not. Today, I want to ask, okay, well, does it have limitations? Can it serve as a bug as well? So in neuromotor control, there's this idea that motor action and motor perception are coupled. What that means is when you act on something, you change your perception of it. And when you go ahead and you perceive something, it can change your the way you control your motor action as well. And I think the best way to internalize this is thinking about how babies learn. So they came out the womb not necessarily knowing how to walk or talk, but from observing the actions of others, they can create these new motor functions of being able to walk on their 2 feet. And today I want to talk about how mechanical impedance is actually a part of this motor action, motor perception coupling. And I'm going to do that via 2 experiments, presenting 2 experiments, one in the motor action domain and the other in the motor perception domain. Looking more specifically in the motor action domain, a couple of current solutions to manage physical interaction include compliance and force control and hybrid control, which assumes that you can control both motion, you can control position and force independently, as long as they're operating in orthogonal positions. And this has led to some robotics using direct force control measurements during motion to measure human intent. Some examples are listed. However, I want to take a step back and ask the fundamental question, okay, well, can humans actually manage direct force control during motion and independent of that motion? And what I'm going to show you today is no, they cannot. And the reason is because force is coupled to motion via an impedance term. And we're going to call that controller indirect force control. After giving you an understanding of mechanical impedance's role in motor action, we're going to take a look at how it's played into motor perception. And as Professor Hogan mentioned, a previous colleague of ours, Professor Megan Huber, previously asked the question, can humans perceive limb stiffness from visual observation of motion? And what she did was had subjects sit in front of a computer screen, observe this 2-link manipulator move, and rate its stiffness on a scale from 1 to 7. And she found that subjects could actually correlate their stiffness ratings with simulated joint stiffness, which is remarkable considering that, stiffness, an aspect of mechanical impedance, is the relationship between force and motion. And just by looking at a computer screen, you can't gain any sort of, or you inherently only have access to motion information. However, the question still remains how, which is where I came in. And I hypothesized that from this motor action, motor perception coupling, the simulated motion that Professor Huber showed her subjects must be congruent with the human's internal model of motion. And the question I'm going to, which I asked and answered, and we'll show you today is, okay, well, what motion cues do humans use when estimating stiffness? So just to give a high-level overview of my presentation, I'm going to specifically ask and answer 3 questions. The first, in the motor action domain, can humans manage direct force control during motion? The second, in the motor perception domain, what motion cues are humans using to estimate stiffness? And lastly, is mechanical impedance a bug or a feature? So taking a dive into the first experiment in the motor action domain, I specifically aim to test the idea that humans do direct force control. And what I mean by that is humans may have some sort of commanded input force that directly goes to the output force. Now, there may be a set of forward-path dynamics or noise that I have not included in the equations here, or those can be corrected via feedback. The key hypothesis, though, is if people are doing direct force control, errors in their contact force will be independent of motion. And if this hypothesis turns out to be false, then that leads us to this indirect force control, where the key component is this position-dependent impedance term. So what do? We specifically asked subjects to apply a 5-Newton force on a robot manipulandum as it moved on the tangential direction of the robot manipulandum as it moved in an elliptical path. That's shown here, and it's important to emphasize that this robot handle is providing its own motion. The human is just trying to apply a constant force on it. And at a given trial, the robot manipulandum went around the ellipse 4 times. And furthermore, the experiment was split into 5 blocks, each consisting of 15 trials. And in those blocks, they alternated between not giving visual feedback and giving visual feedback. And that visual feedback was shown here, where subjects had the static white bar with their target force of 5 newtons, and the moving red bar was their actual force. But the key takeaway here is that given the 15 trials of 5 blocks and the 4 trajectories around the ellipse for a given trial, subjects traversed this ellipse 300 times by the end of their experiment, which will become important later on. Additionally, we were able to obtain data from another colleague, Pauline Maurice, who ran ran a similar experiment, and part of her experimental conditions were exactly the same as ours, except she asked subjects to apply a 0-Newton tangential force in 1 block consisting of 10 trials with no visual feedback. More importantly, though, the key component of Maurice's experiment simply asked, okay, well, what velocity profile should the robot manipulator follow to best enable human interaction? She quantified this with the ability to apply 0 newtons of total force. And her study concluded that the velocity profile should follow this 1/3 power law relation, which is essentially mathematically saying that tangential velocity is equal to the raised to curvature to the 1/3 power. But rather than think about this mathematically, the best way to internalize this phenomenon is that you're moving slower around this, or you're moving faster around the straight edges and slower around the curves. And this velocity profile has been throughout the literature been found to be vertical and consistent with a lot of upper limb reaching. So as Marissa et al. Found that this velocity profile best enabled interaction in her study, we incorporated it in our study as well. So taking a look at the results of the study, what I'm showing you here is the root mean square force error from the target force of the 5 Newton experiment, from 5 Newtons in the 5 Newton experiment and 0 Newtons in Marissa's 0 Newton experiment. And this is separated by a block as a function of trial. And the blocks in purple denote the block are the blocks where subjects were given the visual feedback that you saw on the previous slide, denoted by the V here. So you can see the means across subjects by the yellow dots, plus or minus 1 standard deviation by the shaded region. And then this red line is a linear fit that was fit to the data. And what's important here is we calculated the correlation coefficient using this linear model. And we ran a statistical test to determine if that correlation coefficient was statistically different from a null result of 0, specifically looking to see if it was statistically negative. And what we found is it's only negative in the first block, which says that, okay, learning only occurred in the first block, which if we take a step back, makes perfect sense. Subjects in the 0th block, they were given an opportunity to become familiar with the robot manipulator and how it moved. In this next block, they're given visual feedback. And from the visual feedback, now they can reduce their error. However, the second takeaway is that despite extensive practice, remind you, at this point, subjects who traverse the exact same ellipse 300 times, subjects cannot reduce their force error to 0. So the question comes, okay, well, why can't subjects reduce their error to 0? And the answer to this is periodicity. Now, recall the hypothesis from the direct force control formulation. If subjects are doing direct force control, errors in contact force will be independent of motion. And what does that mean? What does that look like? So if we took the force function, if we took out their force as a function of position, as a function of phase, and we took the autocorrelation of that signal, what we would see if this hypothesis was true is that we'd see something that looks like this flat spectral density here. However, if this hypothesis turns out to be false and there is some sort of periodicity, we'd see this attenuating sinusoidal signal. And in fact, that is exactly what we do see. So here is a representative subject in the 0th block and the last block, and we see their force as plotted as a function of position, and we see the signal is very periodic. In fact, when we run the autocorrelation, we see that there are peaks around 180 and 360 degrees. So the key takeaway here is that force errors are not independent of motion. In fact, this result is actually quite robust across both experiments and across subjects. And here we show histograms of the largest peak in the autocorrelation function and its max peak lag. We see this cluster is centered around 180 and 360 degrees. And more importantly, we note that the max peak lag occurs at 0.45 and 0.41, and these clusters are statistically different from the null result of 0, suggesting that this is not just a random artifact we are picking up, rather this is significant. So the key takeaway here is that force errors are position dependent. So then we can conclude from seeing that, despite this extensive practice, that subjects could not reduce their force error to 0, and this when asking them to do this direct force control task. We can conclude that direct force control cannot describe this phenomenon. Rather, they're using this indirect force control method that incorporates this position-dependent impedance term. Remember that the force error was coupled to position, which suggests that humans do not directly control force. Rather, control of force is coupled to motion due to impedance. So now with the understanding of mechanical impedance in the motor action domain, we can go ahead and draw upon that motor action, motor perception coupling and say, okay, well, can we perceive an aspect of mechanical impedance? And what we specifically chose to look at was stiffness, the relationship between force and displacement. And what Professor Huber previously did was she had subjects sit in front of a computer screen, observed a simulated tooling manipulator move and rated stiffness on a scale from 1 to 7. And subjects watched 30 simulations with 6 different elbow conditions, or 6 different joint stiffness conditions, and rate their stiffness. And as we said previously, they're able to actually positively correlate their stiffness ratings with the simulated stiffness, which is remarkable. They're solving this F equals KX equation with just X. You're finding K with just X. And the question remains, right? And to answer this question, we should take a look into the underlying controller that was used to produce the simulated motions. So the two-link manipulator was modeled as an arm moving in the vertical plane, subject to gravity. And so it had the typical arm dynamics, but the control law is shown here. It may seem somewhat complex, but if we really break it down, it's quite simple. In fact, we have 2 impedances acting as separate attractors. One attractor is pulling the end-point of the hand about this circular trajectory. And then the second attractor is this joint space attractor, which is pulling the shoulder and elbow joint, if you will, to a nominal position. And what's important here is that what was modulated in this experiment is this KQ term here, this joint space attractor. And when asking subjects to do this task without directly telling them, what we were trying to see is, can they tease out differences in this KQ term? So as we said, they could. Professor Huber proved that. The open question is, well, what motion cues are humans using to estimate stiffness? More specifically, are they looking at just path information, meaning displacement, or is temporal information, its derivatives or velocity important as well? And to tease out this question, we ran a set of new experiments where we kept the path information the same as in Professor Huber's experiment, and we manipulated the temporal information. And the way we did that is we called upon this power law relationship that Maurice et al. Previously explained. So remember, there's this power law relationship where the tangential velocity is proportional to the radius of curvature to the 1/3 power, and this is considered vertical. And this is the velocity profile that was consistent with Professor Huber's original experiment. So I hypothesized, okay, well, manipulations of this velocity profile that violate this manipulations of the velocity profile that violate this vertical power law should inhibit subjects' ability to estimate stiffness. So what I present here are 3 new experiments that do just that. In the first experiment, we set this beta constant equal to this beta term, this power to 0, which essentially simply states that the tangential velocity is constant around the entire trajectory. And in another experiment, we set the power to the -1/3, which creates this reverse velocity radius of curvature relationship, where now subjects are going slower along the straight edges and faster around the curves, the opposite of what is vertical. And then the third experiment completely violated the power law relationship. And what we found, in fact, was pretty remarkable. Despite these manipulations to the velocity profiles, subjects could again positively correlate their stiffness rating with the simulated joint stiffness. And here we see the individual subject data. And for each subject, what was done was we fit a linear model and used the coefficient of determination of that model as a measure of subject's ability to estimate stiffness. So here we can see a subject who did the task quite well, as opposed to someone who did not do the task as well. That's quantified by that lower coefficient of determination. And then upon comparing the coefficient of determination across experiments, i.e. the different velocity profiles, we found that this velocity profile had no effect on subjects' ability to estimate stiffness, again, falsifying our original hypothesis. So in conclusion, what have we shown here? And first, we have shown that from this motor action, motor perception relationship, humans can correctly infer changes of limb stiffness from non-trivial changes in multi-joint limb motion, which suggests that stiffness or an aspect of mechanical impedance is encoded in subjects' perceptual model of this task. Again, drawing upon that motor action, motor perception relationship. Secondly, we showed that subjects can make these stiffness estimates based regardless of the velocity profile, or despite manipulations to the velocity profile, which demonstrates that path information, specifically displacement, is predominant over temporal information in this task. And I think this work has 2 key impacts. The first is that we have used a perception experiment to poke a little bit more about the latent motor action controller. Again, tying into this relationship between motor perception and motor action, showing that mechanical impedance is a part of this coupling. And then lastly, this method, which I think is pretty interesting, suggests that there could be a new minimally invasive technique to measure stiffness, right? So currently to measure stiffness, or more generally impedance, you must apply a force and measure the resultant motion. And that can be somewhat invasive, right? But however, presently there exist many methods of non-invasively obtaining kinematic data from pose detection softwares. And if we can figure out, okay, well, humans can use kinematics to estimate, only kinematics alone to estimate stiffness, well, maybe we can build a software system that can do that too. So lastly, I wanted to talk about, okay, is impedance a bug or a feature? And quite frankly, my answer to that question is both. If we take a look at the original direct force control experiment in the motor action domain, impedance is what inhibited subjects from doing that task. But when we look at the visual perception of stiffness, this can serve as a feature. And I think the best way to think about this is in human collaboration. And I think the most intuitive example is if you go to shake someone's hand, there may be a power dynamic there, and it's that you don't want to grip their hand too hard or you don't want to grip it too soft. And before you go and feel the grip force of their hand, you can actually kind of tease out what their grip force is going to be by just visual perception of their motion, leading to an understanding of that stiffness relating to the force, and you can appropriately apply an appropriate grip force in response, just from that visual perception. So why does this matter? I think the biggest takeaway from this talk is that when working with humans, impedance is going to be very important. It's going to exist, whether you're in the action domain or the perception domain. And it's important to understand that how you can exploit it and use it to your advantage, or how it can be misused. And you don't want to misuse it, essentially. And taking the previous example of human-robot physical interaction that motivated this talk and motivated the motor action experiment, we showed that when you control a robot in a way that is incongruent with the human internal model, the human will have a hard time interacting with it. However, if you understand that mechanical impedance is an aspect of motor action controller, and you take this into account when designing your robot controller, you can exploit mechanical impedance. You can use it to your advantage. So in conclusion, I've shown that mechanical impedance is a part of the motor action, motor perception coupling by one, showing that it is necessary to model. It's necessary when modeling physical interaction by showing that humans can't do direct force control because motion is inherently coupled to force. And lastly, and secondly, I've shown that humans can perceive an aspect of mechanical impedance, specifically stiffness, and their perception of this is robust to non-vertical velocity profiles. And then the biggest takeaway is that mechanical impedance can serve as both a bug and a feature. It's up to the designer to choose to be cognizant of this and to exploit it rather than misuse it. Lastly, I want to acknowledge my collaborators, Professor Megan Huber at UMass Amherst, a lab mate of mine, James Hermes at MIT, and then my advisor, Neville Hogan at MIT. If you have any questions, you can contact me. Here's my email. For now, thank you. Let me know if you have any questions.
Thank you, Michael. Very interesting talk, a fascinating subject, and we are now open to questions.
I have a question. So Michael, first I want to say great talk. I really enjoyed listening to you. And so my first question would be, I think for your first experiment, you showed that you still had this non-zero force error as you were controlling for your experiment. And so I'm wondering, do you think this this non-zero force error could potentially be back calculated to determine the bounds of human control of impedance? So maybe potentially thought of in another way, right? There's the minimum force error that you see from your first experiment. Do you think that could be back calculated to say, well, humans can only control, let's say, their stiffness within plus or minus 5%, or their damping within plus or minus 5%, something like that? Curious to get your thoughts on that.
Let me think. It's tough. So I think, this screen is what you're viewing. So inherently, if we're assuming this direct force control method, what's coupling the position to force is this nominal trajectory, which we often coin the zero force trajectory. And that's ideally somewhere along the forward path, the motion that's being controlled.
Mm-hmm.
And if we were to go ahead and basically say, can we solve this equation for Z? The biggest issue for finding this, for solving this equation is we don't necessarily have any idea what this zero force trajectory is. I think a lab mate of mine, James Hermes, has worked into kind of understanding aspects of that. But I don't think I'm not sure how far along he's gotten. It's not published yet. So
For sure. Yeah, absolutely. No, I appreciate it. Great talk. Really, really appreciate it.
Thank you.
Alison, you have a question, so maybe you can ask directly.
Sure, I put it in the chat, but I'll ask directly. Can you hear me okay?
Yeah.
Yes.
Great. Yeah, so this is really, really fascinating. Thanks for the great talk. In the perception experiment, I was curious whether it matters that the virtual robot arm kinematics and maybe dynamics are sort of similar to the human arm, or at least 2 degrees of freedom of it. And I was wondering if you did this with any mechanism, can people figure it out, or are they somehow relating it to their experience of human mechanics?
Yeah, so that's the key hypothesis, is that they're relating it to their experiment with or their experience with human mechanics. And I believe Professor Huber tried it with a 3-link manipulator. And the idea was that maybe it looked something like a finger, but the motion didn't seem too biological. So I don't believe there was any results on that experiment. But the key hypothesis is that, yes, subjects are trying to make estimates based off of what they understand about their own motor controller. And in fact, what we did was another aspect that I didn't get to present here, but we asked subjects to write down, like open-ended after they completed the experiment, to write down what it is that they use to estimate stiffness. And some subjects immediately did say, oh yeah, I thought of it as an arm, and I think about like my arm motion. And other subjects didn't necessarily say that at all. And we didn't quantify whether or not subjects specifically said they thought about it as an arm and how that related. But most of what we did quantify is whether or not subjects are looking at past information, temporal information, joint motion, or endpoint motion. And our results in this realm were fairly inconclusive in the fact that regardless of what subjects said they were looking at, it didn't necessarily reflect on how well they performed based on our performance metrics. So to answer your question more succinctly, it's hard to basically tease out.
Thanks.
But
Great.
my key hypothesis, yes, subjects are using what they know about their own motion controller.
We also have a question from Greg.
Yeah, I can go ahead and say it out loud also. This is Greg from Georgia Tech. Really awesome talk. This is a little bit of a piggyback off Allison's theme, which is the idea of the internal model. And I wonder if you place a participant in an environment for some longish period of time where there is an intentional impedance between them and the manipulandum, and then you remove that, or even if you leave it on, would you expect the performance to change? Just the idea that, are there ways to kind of examine mechanistically whether or not this is strong evidence of an internal model formulation?
So I guess your question was 2 parts. And
yeah, sort of.
I'm not sure I fully comprehend the second part, but I'll answer the first part and then let you re-explain the second. But the first part, yeah, people have done sort of adaptation studies to see, okay, how are subjects going to adapt to different like force fields, force perturbations, and so forth. And actually, one aspect that I think is really interesting was a talk we saw by Aaron Batista over at Pitt, and he did it his work, he worked with monkeys, and he specifically showed that there's a manifold in which you can retrain a neural adaptation. So you can retrain, the monkeys have some sort of, I'm going to misquote this because that's not my area of expertise. They have some sort of implant in their brain that allows them to control a cursor on the screen. And he's figured out that there's a manifold where this is done naturally. And if you try and get them to do something orthogonal to that manifold, it is very, very hard to adapt to. So that's a work that I think is pretty interesting. What was the second part of your question?
I guess I'm just wondering whether that, like those adaptation experiments where you expose someone to a new environment actually change perception too, right? Like, does that, if I trained in a new environment, would that reduce or increase potentially my ability to estimate stiffness from motion? I'm guessing that it could interact in bad ways if I'm relying on my experience in the world up to that point and using that knowledge to project motion to K. If I have even a short-term change in the environment that I'm reacting to in terms of model reformation, then maybe my perception also gets messed up just for a little while. Yeah,
that's actually a really good question. I've never thought of that. I never thought of that. It's interesting you bring that up because I think the key question is, well, how much would you have to change? Like, maybe have them do some sort of reaching task in the real world, and then immediately have them do the perception task, and then have them do something. And the question is, well, is their perceptual model built based off of years of experience, or is it just the most recent experience they have?
Yeah, exactly.
I don't know.
Thanks.
Well, thank you so much for to the speakers and all the participants. It has been a very interesting session, and stay tuned for the next one. Have a good afternoon. Bye.
Thank you.